My name is Chung, and my student ID is 11331131. My topic is visualization of atmospheric pressure with a soda can. Atmospheric pressure, or core air pressure, is the force applied to a surface by the air above it as gravity pulls the air towards the earth. The air around you has weight and exerts pressure on all surfaces it encounters. It is commonly measured with a barometer. In a barometer, a column of mercury within a glass tube moves up or down in response to change in atmospheric weight. Then why can't we feel atmospheric pressure? It's because the air inside our body exerts the same pressure outward, resulting in no pressure difference and no need for us to exert any effort. We know that air is colorless, odorless, and tasteless. Air freely expands and changes shape according to the container or environment it occupies. We have to feel air pressure because the air inside our body exerts the same pressure outward. Therefore, we observe air pressure by question can experiments, providing a tangible representation of how pressure differential can impact physical objects. Here are the materials: an empty soda can, ice water, heat source, and tongs. Here are the objectives. Illustrate that atmospheric pressure exerts a significant force on object, and highlight how a difference in pressure between the inside and outside of a container can lead to physical change such as deformation. Step 1 is preparation. Ensure the soda can is empty and add a small amount of water. Prepare a bowl of ice water. Step 2 is heating. Place the can on a heat source and heat it until the water inside boils and steam is produced. When the water inside the can boils, it changes from a liquid to a gas, pushing the air out. This process pushes most of the air out of the can. Step 3 is inversion. Invert the soda can and submerge it in ice water. Water seals the opening of the can, making it airtight. The water vapor inside cools and condenses back into liquid form, and the result is the soda can deforms rapidly with just 0.16 seconds. Here's the principle. As the water is heated and boiled, steam displaces the air in the container above the water. When the soda can is plunged into cold water, the vapor condenses quickly, turning into a few drops of water. This liquid occupies much less space than gas, creating a vacuum inside the can. At this moment, the outside air pressure is significantly higher than the pressure inside the can. In nature, systems tend to seek equilibrium, so this imbalance causes the can to be crushed until a new balance is reached. The resulting large discrepancy between the outside and inside air pressure generates a substantial net inward force on the can, leading to its vapor crashing. The experiment supported by ideal gas law, PV equal to nRT, is simply the combination of all simple gas law, Bohr's law, Charlie's law, and Avogadro's law, demonstrating the relationship between temperature, pressure, and volume for gases. And from this equation, we can see that pressure affected the volume. Let's talk about the deficiency of understanding the phenomenon without visualization and high-speed photography. First is how to grasping complex concept. Air pressure can be an abstract concept. Without visual representation, it becomes challenging to understanding the dynamic nature of pressure change. The second is how to understand the impact of pressure imbalance. A visual representation can show the pressure difference before and after the can is plunged into cold water, making the concept of pressure imbalance more tangible. The third is less engagement and retention. Visual aids enhance engagement, making it easier to retain information. A lack of visual can lead to a disconnection between theoretical knowledge and practical application. How this project helps understanding the phenomena. This experiment clearly demonstrates how the internal low pressure in the can combined with the higher external pressure crush the can, allow us to directly observe the pressure of air, moving beyond theoretical understanding. The experiment provides a tangible way to see the effects of pressure difference on objects, helping us make connection between the concept of air pressure and real-world phenomena. High-speed photography allows us to slow down the crushing process of the can, enabling clear observation of every detail of the transformation. This enhances the learning experiment and helps us understand the principle behind rapid events. Here is the reference list. Thank you for your listening.